G'day, welcome back to the Big Cubane series, the series where we're trying to make a lot of a molecule called 1,4-dicarboxyl cubane because it's cool, and if we have a lot of it, we can do some cool experiments with it. We did this whole scheme, a couple of years ago now, but we know it works because we got a small amount of cubane at the end of it, but now we're scaling up. And where we are at the moment is we've completed step 3, which is good because step 3 was one of the more complicated steps. I was really worried about scaling up, but we have quite a bit of this tribromo product, which is the end of step 3. So now we have, I don't want to say the word easy, but let's say simple, 2 simple steps, and then a really hard step. So we've got step 4 and step 5. Hopefully, we get these done reasonably quickly so that we can move on to step 6, which is the really difficult step, the step that will require some engineering and some luck and, some favor from the gods. Whereas the other 2 are reasonably straightforward. We've got the Stills-Alder step where we've just got to reflux our product with some sodium hydroxide and ethanol, which makes these 2 molecules kind of combine, and we get rid of a lot of our bromide, and we end up with this material, which when we ran it last time just worked straight away and made a really nice pure product. And then we have this step, this double deprotection step. This step takes a little while, but it seems to work pretty well, and the product we get was reasonably pure and actually wasn't that pure, but it purified out pretty well from what we saw. So I am not too worried about these steps. But then again, it's always the steps you don't worry about that sometimes catch you out. So we've got to do these steps good and well so we have lots of material to start step 6 with. Because if we can nail step 6, I'm really confident in this whole procedure. But we need to make a lot of stuff and get to step 6 well. That's our goal. So yeah, that's it. That's the whole introduction. Let's get on to do some chemistry because I originally said when we started this project that I wanted to have the 100 grams of cubane at the end by the open source convention, which is in mid-July. And it's a little bit optimistic to think that we're still going to make that, but, we got to work to deadlines. I don't work to anything else but deadlines, so we got to get a move on. And it starts with nailing these next 2 steps. Let's just hope we do good. Let's just not stuff it up, all right? Let's get on with it. Here we are. Not only is this one of the most reliable and easiest steps, but it's also potentially the cheapest step because we're just refluxing our material with sodium hydroxide in ethanol. Now, I can get ethanol from the hardware store. This cost me a little over $5 for an entire litre. It's 95% ethanol and with a little bit of denaturants in it, so you can't drink it. Doesn't stop everyone. There's no methanol in it yet because I think at some point they did put methanol in it, but the people that would drink it anyway would then get severely blind and poisoned from it. So now it's just very unpleasant. Anyway, what am I saying? Sodium hydroxide, you need about 100 grams of this. I'm going to use a whole litre of ethanol, and we have our material here which has been sitting in the alfoil just so it doesn't decompose so much in the sunlight. There's 170, 150 grams. We can do this live. Yeah, I can't do maths, but yeah, sure, there's some amount of it in there. That's great. So we'll set it up to reflux in this 2-litre flask. We've got to add the sodium hydroxide to the ethanol somewhat slowly so it doesn't all overheat. So I'll add half of that right now. No delays anymore. We're on a bit of a timeline. Let's do it. Fucking had to spill some of the end, didn't I? I was trying to be cool. That's my problem. I gotta stop trying to be cool. I really gotta stop trying to be cool. I gotta just try and be good for once in my fucking life. I could be good instead of cool, but no. Gotta do it with flair. Immediately goes yellow. What's new? Okay, so I've dissolved 50 grams of sodium hydroxide. It takes a long time for the sodium hydroxide to dissolve in the ethanol, and I'm still not entirely convinced it's all dissolved. It took about 2 hours of stirring to get to this point. Got another 30 grams for a total of 80 grams of sodium hydroxide. The amount of sodium hydroxide doesn't really matter. It's not really that crucial. We just want lots of sodium hydroxide basically in that ethanol, and that's why I'm not really caring too much about the ratios. All right, let's talk about our brominated stuff. We have, from last video, made 170 grams of this tribromo ketone. But look at this. So I don't usually do this, but I noticed after last episode we got we got okay yields, but not great. But then I was adding a bit more water to the old bromination solution, and a little bit more product was crystallizing out. So I continued that, and I ended up getting another 76 grams of tribromo here. A little bit more yellow, so you could say it's a little bit more impure, but it was pretty good. Actually, it started oiling out a little bit, which is kind of a sign of it not being super pure. So I ran a recrystallization from ethanol, and to make sure it crystallized out nicely, I used a little bit of this nice product to, seed the crystals. I actually used quite a bit of it. So all up, we ended up with about 237 grams of tribromo, which brings us to a 66% yield on the bromination step, which is much nicer. So all this extra stuff definitely is needed for what we need for this large-scale cubane situation, and it all should be able to go into this flask. It was a bit weird doing like cubane chemistry off camera for this. Actually, it was pretty uneventful, but during the recrystallization, so it was hot ethanol with a lot of this tribromo dissolved in it. Some actually splashed on my hand, and these are my nitrile gloves, and these are my sort of shitty, cheap latex gloves, which I occasionally use for chemistry, but generally just use and throw away a lot because I've got to like touch a phone and a camera and lots of things. Anyway, the ethanol and bromo stuff just instantly penetrated the glove, and it didn't hurt or anything, but for the next 2 weeks I had these horrible bromine stains, or like bromination stains on my hand, which I wasn't too impressed about. So yeah, I gotta be a bit better at wearing the better gloves. I mean, it might have penetrated these other gloves anyway, but yeah, it's not often I end up with physical scars from the chemistry, I've got to say. God damn. It did fade, skin's pretty good, and I don't think I was poisoned that much, but anyway, pointing it out, as soon as you do something off camera, it's kind of, I'm like, now nothing exciting will happen. I'll do this all off camera and then instantly injure myself. It's fine. You don't want to see me get injured on camera anyway. It's fine. All right, so let's move this forward. Shit. Now I definitely not going to get injured for the rest of this video, because if I do, then that sentence will come back to haunt me. Let's get the rest of this sodium hydroxide dissolved in this goddamn ethanol, and then, yeah, we'll just add all of this. We need to reflux for 3 hours, which is not particularly long, and then we need to dump it into a large amount of water, which will wash off the sodium bromide, which is a byproduct, and leave us with our nice organic product, this Deals Older product. Yeah, we need quite a large volume of water. I've got to actually find probably a literal bucket, so I'll do that. But apart from that, I think we're all good for a montage, so I'll see you on the other side of this. Bloody hell, let's go. Let's get this done. Look, what are you doing? What are you doing? Oi. Come on, little guy. No, you can't live here. No. No. This is going to be heated. It's going to be heated. You can't live here. Come on. Oi. Mate, come on. Oil. Calm thoughts. Two stir bars in there? That's not gonna work though. Some product, sort of. Alright, and after all that, we're left with this bright orange powder. Sunlight absolutely beaming in. It's not meant to be orange. It's not good that it's orange, actually. Even our previous runs, we called it a slight beige colour, a slight off-white. This is bright orange. I do have my old stuff. I believe this was after recrystallization. It looks pretty good. And Chemiolus sent me this sample, a couple of samples that he made, and I think he recrystallized his as well. But anyway, looks very nice, and it should be a lot nicer out of the reaction mix. It also has a bit of a smell which is reasonably reminiscent of the starting material, so I think that's what's happened, is we just haven't had a complete reaction. It's still quite wet as well, but I reckon it's worth just putting this back and doing the same reaction again, putting this in the ethanol, adding more sodium hydroxide and refluxing it for longer, because if this is just tribromo left in the product, we can convert that into the product and also clear up the product of all this stuff. So more off-white product than bright orange. Yeah, there's a reasonable amount here, but yeah, it's just completely awful looking. There's also a little bit more. I mean, filtering all this was obviously quite difficult, so I let a lot of it settle out and then poured off all this and then filtered the stuff through. That was just most of it down the bottom, but there's obviously still a little bit left in here, so I'll try and catch this, but it's probably only 5% of it. But yeah, I should really dry this out as well. It's quite wet, and before it goes back in the ethanol reflux, should be reasonably dry before doing that. It doesn't have to be particularly anhydrous or like completely anhydrous, but having a lot of water in that refluxing reaction might cause some weird products to form, like breaking off those protecting groups off the top or something, which I'm a little worried about. So yeah, just get this reasonably dry without decomposing it, and then put it back, just do it all again. Do it a second time. Hopefully it comes out better. Yes. After all that, we're left with, I mean, it's practically the same colour. I was going to maybe say it looks a little bit better, but honestly, it might look even a little bit worse. Less orange and more brown. What's the technical term for this? Pooey. You know, looks like shit. Yeah, look, I could run a recrystallization. I think it should be okay. It's a little bit more crystalline than it was before, but luckily we didn't lose too much yield. It doesn't look like in this redoing the reaction with the same material. I need to dry it out quite well before I weigh it, so I'm going to have to put it in desiccator overnight. But yes, so recrystallization, I could do a recrystallization to purify it, and this is what I've done in the previous series on the smaller scale. But the next step, when we're making the double deprotection molecule, so we're putting in concentrated sulfuric acid, I think we should do the purification after that step. That will stop us losing some product in our purification step, and the next step is so harsh anyway. I mean, I think any tarry contaminants might get burned up by the sulfuric acid. Anyway, that's what I'm optimistically thinking. We're going to have to do the purification there anyway, so I think we will continue ahead with this, even though it looks quite brown and tarry. There's a hint to what might have happened in the 1989 Navy report, which we reference quite heavily, and it says that if tribromo with even 10% of dibromo is used in this reaction, the final product is dark and tarry, or something along those lines. So I think I got a little bit greedy, and when I separated off more tribromo and said, oh, the purity is a little bit bad, but it should be okay, I think that probably had a significant amount of dibromo in it. And when I say significant, I'm saying, maybe 10, 15%. So overall, 10% of the dibromo has led to this product being quite dark and tarry. But I think majority of it is fine, so we should just keep going on to the next step, and I think hopefully we should be okay. Okay, let's get this in the desiccator, and then we can dry it, and then we can actually determine yields before I'm sad about anything. Let's get the numbers to be sad about rather than hypothetically sad. Okay, here we are. Couple weeks later, actually. It's been in the desiccator a long time, so it is very dry, nice and crystalline, and it is 103 grams, or just over 103 grams, which represents a 78% yield. I'm actually very happy with this, especially considering the fact that we ran the reaction twice. 78% yield is pretty good. I mean, I think it's a relatively high yielding reaction, and if I looked at what other people got, they probably got higher numbers, but especially on such a large scale, because the mechanical losses were quite high because I had such a big volume of solution I had to pour pour around and, you know, a bit of spilling. 78% I am pretty damn happy with. You could say it's all impurities because it's kind of a nice caramel color. It's a bit orangey. It's nearly a delicious color, kind of brown sugarish, but it's pretty crystalline, and I'd say that there's really not that many impurities in there, so it should be okay. In saying that, there's definitely a hair in there. Hold on. What's the hair doing in there? One impurity removed. I've removed all the hair from it. But yes, it's great. 103 grams is a lot more than we made last time, which, once again, I keep saying it's great, but it's not that great. The point of this series is to do large scale, not medium scale. And 103 grams, I mean, we want 100 grams of cubane at the end of it. And we lost a lot of mass between our previous product and this product, and that's because about 40% of that previous product, the tribromo, is just bromine. So we throw away 2 out of the 3 bromines, and that gets converted to sodium bromide, and we wash that away. So much of the mass of the product is lost. So, you know, percentage wise, we've got quite a lot of the product, but we lose a lot of mass in those bromines, and that's going to continue because we throw away those last bromines later on as well. So to get, even if we have very good yields from now to the cubane, which we're not going to do, but even if we did, we're still not having enough product here to make 100 grams of cubane. So we need to make more. We need to make more. Before we do this next step, which should be relatively simple, although quite time consuming, I want to make more of this. I really need to make more of this. But you say, how do we make more of this? We've just spent the whole series making this, and we've been using all the product all along. Well, in the background, I've kind of been running a second synthesis because I thought we might get to the point where we start to have low amounts of material. So I've made some other stuff. I had to go all the way back to cyclopentanone and make some more cyclopentanone ketal, which I did off camera, made some more dioxane, and I have leftover bromine. So I have hopefully enough bromine to do another full-scale run of this, and then we can run the Diels-Alder reaction again and end up with another 100 grams or so of that. And then we can do this next reaction with 200 grams. So I'm going to try and quickly smash it out. We've already done the bromine reaction before, so I'm not going to film it too much. I mean, I did the cyclopentanone reaction for the second time, and I didn't really film any of that, but I just did it because I just wanted to see if I could do it and do it quickly, and it was pretty uneventful except for one bit where I didn't add very much sulfuric acid when it was like refluxing in the Dean Stark setup, and then I decided to add a little bit more, so I let it cool a little bit. I thought it cooled a lot, and then I added in some acid. It sucks that now I'm just having to describe what happened to you rather than filming it, but when I add the acid, the whole thing like flash boiled and it went and it sprayed the walls and everything with toluene. This was like 2 months ago, but this got quite damaged, and even the paint, I mean, it looks pretty bad normally, but it got much worse after having toluene and cyclopentanone and everything sprayed around. There's a video on Camolius's channel where another reaction does a similar thing to what mine did. So this is a recreation of kind of what happened. Yes, so I lost some yield that way. I feel a lot less stupid when things like that happen on camera because at least it's content. But when that happens off camera, I'm just like, I wasted all this product and everything, you know, I contaminated the lab with solvent for nothing. But anyway, we got some nice dry cyclopentanone ketal. So let's run another bromination step. Let's see if I can smash it out. Let's go. And then we can come back and do this next step with even more of this. And hopefully I can do it better. It's hopefully less orange. I hope so. Alright, here is our new tribromo. It was on a little bit less of a scale, so slightly less cyclopentanone ketal put in because I had slightly less bromine, and I think the yields are quite a bit lower as well. Well, I know the yields are quite a bit lower, and that's probably because of all the bromine I spilled. But the product we do have is looking great, so we can now run this Diels-Alder reaction, a reaction that I've run 2 times already this video. Hopefully I'm doing nothing wrong with it, because otherwise I would have done the same thing wrong 3 times in a row. Anyway, let's do that straight away. Let's get to it. You know, no time to delay. Let's run this reaction and we'll come back when we finally have lots and lots of Dill's older product. Whole new batch. Hell yeah. Looking good. I just need to filter this 8 or 9 litres of liquid. Looking good though. I mean, it looks like mold. Looks like moldy tea, but it's good. It's good. It's what we want. And here it is, more of the Dill's older product. Do you like my orange gloves? I thought they would be fun, but I put them on and immediately started feeling like dank pods. You know, gonna arm that nug. I can't do his accent. He's too Australian. This is great. It's only 54.4 grams of product, which gives us an overall yield, well, the yield of the 2 steps from that key towel to here of about 28%. In contrast, this batch is 100 grams, and we started from the same amount of key towel between these two, so really there's an overall, I mean, it was slightly different, but an overall yield for those 2 steps of 53% or 52 or 53% for this one. However, you know, something does come to mind when you compare these 2 products. Yeah, this one is quite nice. This is kind of what I'm expecting it to look like. This is tarry. So really the loss of yield is because I didn't scrounge much tribromo, so I didn't collect as much dibromo and carry that through the Dill's older product, which I think is what's causing this tar. But also the sort of involuntary spilling of so much bromine probably caused the overall product to be unbrominated, but, you know, only the tribromo crystallizes out initially. So, yeah, I think that's what's causing our low yields for these 2 steps, because the Dill's older step, the step that we're actually meant to be doing in this video and focusing on, is fine. So, no issues there. But anyway, so now that overall we've got just over 150 grams of material to go on with to finally do this second step for this video. I can't believe how long it's taken. It's been like 3 or 4 weeks since I had made this, and now I've got 1.5 times as much, but it's cost me 3 or 4 weeks. This is not going at all well. I said weeks and weeks ago we have not much time, and now we have really even a lot less time. Anyway, I'm yapping on about not having time. God damn, we have to dissolve this in cold, concentrated sulfuric acid and stir it overnight. I was going to collect them all together because we need a reasonably large amount of sulfuric acid, but not a gargantuan size of sulfuric acid. So it will still fit in a 500ml flask, I think, if we combined all this together, or maybe just. But given the fact how tarry this one is and how untarry this one is, how untarry this one is, I might separate them into 2 batches. So we'll run the same reaction at the same time, but in 2 different flasks, just in case this one really does go awful. But yeah, I mean, I'm complaining about tar now, but you ready for the sulfuric acid I'm going to use? A lot of you would know what the sulfuric acid already looks like, because yes, we're using drain cleaner as is. Should be fine. I think this is what I used last time. It was fine. So drain cleaner as is. Let's get it out and have a look at it. Also, actually, first I gotta clean up this area. My gosh. There is no more space to do chemistry in here at the moment. And it just keeps going. I won't show it all because I'm embarrassed, but oh man, let's clean up. I can't believe I've taken this long to do the reaction and the place is still dirty. Like, I could have been fast and messy or slow and clean, but I was slow and messy. It's terrible. Anyway, moving forward. Isn't this beautiful? This is MoFlow liquid drain solvent. Yeah, sulfuric acid. 1.83 grams per mil. Concentrated sulfuric acid, very dense. This is about 300 grams. It's about 550 grams of sulfuric acid, so they're quite heavy. Oh, even the clamp with the brick on it is... Ooh, that's not nearly as balanced as if this was like over here, then yeah, God, okay. Gonna need bigger bricks. Balance these clamps. The water bath is here because we need to get these cold, and we want to add all our Dill's older product into here while it all stays cold, and then we can let it heat up. Got some stirring here, you know, that I'm trying to vaguely share between these 2. So a little bit to sort out, but this is what the sulfuric acid looks like straight out of the bottle. Shouldn't be this dark, but it's got some dye in it. I think I'm going to call it dye because that makes it sound like it's not a big deal. If I just say the sulfuric acid has tar in it straight out of the bottle, it doesn't seem as nice. But let's get this cold. We need to get this cold. I've only got temperature reading in this one, so I'll keep reading the temperature in this one and assume that they're the same, which is a terrible idea, but we're going to do that anyway. Also, I did a terrible job of cleaning up this area. Alright, everything is looking nice and cold. We've got the 2 flasks here. I've got the frowny face one. You can't really see that. Frowny face one for the tarry stuff, and the smiley face one for our slightly nicer but still yellow one. It looks all good, so we're set to go. We need to add in our powders into the mixture and then keep it cool. We don't really want it getting, you know, above a couple of degrees, which is why we've got all this ice. But once it's all added and stirred for a little while, we'll let it warm up to room temperature, which isn't too hot, and then let it stir there overnight. Before tomorrow, we dump it out into some water, and we should be recovering our nice product from there. It should just be a nice solid and all that. So nothing too stressful, even though usually with this much sulfuric acid and this much ice, you have a reason to stress because it feels like I'm doing a nitration or something, which are a lot more stressful because, yeah, when you start adding stuff, it gets so hot so quickly. But I think from what I've seen and when we did this reaction last time, the sulfuric acid doesn't really heat up too much when we add in our mixture, but we still got to add it all slowly. We can't just dump it all in at once. And we've got our stirring here. If you're very keen-eyed, you'll see, look, this stirring thing actually tells us how fast we're stirring. It's very weird, but I bought out someone else's home lab, and they were packing up a home lab. I knew them from many years ago, and they packed all their home lab up into a car, and I met them in a bloody shopping market car park and bought all their gear. So I got a bit of extra stuff, and this is the same as my hot plate, but the model up. Like, it tells you what temperature you can set it to, and then it goes to that temperature, and the stirring, it's not just a knob, you like set a number for it to stir. That's amazing. That's incredible. There hasn't been this level of innovation in shed science this decade. That's just crazy. I now not only have one hot plate, I have 2, but one that actually has a temperature dial. Wow, that's amazing. At any point in my life, I could have bought this hot plate. Could have got the upgraded one, but I've just stuck with the base model. Anyway, not to get all too fancy for you, I see these comments that are like, oh, don't buy nice gear. It's fun you struggling. I love to see you suffer. Don't worry. We're still going to suffer, even if it's just marginally easier, because now I can set a temperature. I don't know how accurate it is, but you can actually even put in a bloody external probe in the back. How sick is that? It's not mint condition. But it also didn't cost me that much money, because I bought his entire lab for the cost that it would cost me to buy one of these hot plates brand new. In fact, it was probably less. Anyway, sick. My powers continue to grow. Alright, I'm yapping on. Let's bloody get this done. Let's go. You dense fuck. Come on. Don't tar up. Don't tar up immediately. Come on. I'm gonna do better than this. They're both stirring properly. Finally. 2 hot plates at once. I am powerful now. I am powerful. Don't judge. Alright, and after many hours of filtering, we have 3 lots of solid. Both of these are from the 100 gram run, the frowny face one, and it ended up being a bit of a browny grey solid. And from a happy face one, we sort of browny orange. We got a lot of solid and a lot of piss coloured liquid. The god of tar wears many faces, yet he is always recognisable. Yeah, we're going to have to get these super dry before we start doing the purification step, because I think the water will interfere with the purification step. Maybe not super dry, but I don't want to wash these with ethanol or methanol or acetone because it'll just dissolve too much solid. And we've washed it with a bit of bicarb and lots of water, so we've gotten rid of the sulfuric acid. But it's just a matter of leaving these on the pump to try and draw off as much water as I can and then putting it in the desiccator. But before we get to all that, my mind is going to the next step already. Step 6. This is the little step I'm worried about, but there's 2 paths we can go on. I should draw something on the board, but it just says more cube. There's 2 paths. One path is the flow path, and the other path I will call the jug path, alright? So this flow reactor, we have to expose this solid to a large amount of UV light with a little bit of photosensitizer in it. And the idea is to not let it get too hot and, not overexpose it too much. So the best way to do that is a flow reactor, right? So flow reactor in the sense that you have your liquid, your solid dissolved in a solvent, and you pump that through some tubes. The really thin tubes so that the solvent gets exposed to heaps of UV light because you've wrapped those tubes around the lamp, and then it comes out into another bucket, and that bucket is perfectly filled with solid that you want, well, in the solvent or whatever. So you've done that reaction through the tube, which sounds really good and has the advantage that it's really quite scalable. So even if we had 1 kilo, 2 kilos of this material, we would just have more solid dissolved in the solvent and we just run the reactor for longer. It doesn't really affect how much each molecule gets exposed to the UV because each molecule just goes through the same tube. We just run the reactor for longer. So it's scalable and it's very cool. So those are the advantages. The disadvantage is that I don't really have a good way of calibrating it because I can't really test very well at the moment the end products. If we run it through the reaction and say we only get 60% conversion, how do I know that? Maybe I'd be able to tell, oh, it hasn't fully converted, but how would I be able to tell the difference between, say, a 10% conversion and a 90% conversion? What sort of speed does it go through the tube? What's the path length? I don't know those variables, so I'd just be guessing and hoping I get it right. And it's a lot of engineering. It's complicated. Well, it's not that complicated, but I've got to build this thing, and if I build it and it only gets 10% conversion, what am I changing? Am I building it in a way that it's flexible so I can increase the path length or add more lights if needed? I don't know. There have been some good papers on this subject and some YouTube videos of people doing this exact thing, this Cubane flow reactor. But on the other hand, this jug method where you just put the stuff in a flask and blast UV through it for a couple of days, which is what we did last time, Camolius did last time, and some other people did. And there's even papers now where people are just doing this way with their LED panels. It is simpler, doesn't scale as well, but people are still doing it on a reasonably large scale. And even if we had to do multiple flasks or, a flask and then, do 3 days and then do another flask while we do the other one, it's still quicker than doing this whole build project at a flow reactor. So the jug method has that advantage in that simplicity, in that we can just see that conversion, and if it's not converted and we have a way of saying, testing it and saying, oh, it's not fully converted yet, we just leave it in the reactor longer and then we come back in another day and then check it again. We don't need to perfect these random variables that we can't really calibrate. It's less cool though. It's so much less cool than a flow reactor. So which way do you see me going? Sorry for yapping on so much in this video, but there's just a lot to think about. And rather than thinking, I'm just saying these thoughts out loud because you guys often have better ideas than me. In fact, nearly always you have better ideas than me, but doesn't mean I don't follow my own ideas because got to respect a bad idea every so often. All right, this is fantastic. Let's keep going. Come on. Let's get some dried solid of the diketone, the deprotected diketone. Let's do it. All right, I'm using the big pump to just suck through the last of the water from this sample. It's not the most ideal to pull water vapor directly into this oil-based pump, but she'll be right. She can take it. She always does. It's fine. I just don't want to heat it too much. It sucks to go this far and then put it on a hot plate and then burn it or make it all char up or tar up just because I'm, you know, impatient with the drying. Here we are after a couple of days in the desiccator. We ended up with a 78% yield on the smaller scale, the one that we thought was going to be worse, and on the large scale we ended up with a 92% yield, which is fantastic. We've done it, so we can stop the timer and look at our world record speed run of 62 days for these 2 steps. A lot of things went wrong with these 2 steps, but I can't help but shake the feeling that if I was a little bit more organized, I probably still could have done this all in a couple of days. But then again, if I was a well put together human being, I probably wouldn't be making tiny molecular cubes in my shed. So next up we have the purification of these 2, and then we can bloody put it through the photoreaction, however we're gonna do that. So you better subscribe, and I'll see you all next.
And you know, man, I'll see you all next time.